Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Today, let's talk about the higher order elements. Here, what we mean is that the approximations which we do for each element will be of higher order. Until now, in 1D, we just talked about two-noded element. And in 2D, we talked about a triangle, so where the approximation was just linear, a plus bx plus cy. So those were the minimum, but what about using higher order approximations? So what is the importance of that, and in what way it going to give better results for us? So just to recall, we have the variable phi in the heat conduction, or it can even be u in the case of displacements in solid mechanics. So in any case, so we have the phi. So if you look at the approximation, okay, so let's look at this, the one-dimensional approximation where phi is a function of x, and using Taylor series, approximation, so we know that this can be approximated as phi x naught. So this approximation is, let us say, phi. So x can be written as x naught plus delta x. So this is what we, and continuing this, so like this we can go up to pth order. And so on. So if you are, let's just see, if you are doing up to x to the power of p, then there are higher order terms, which we will call it as approx errors. So now let's, instead of this x naught and all that, just for the sake of simplicity, so let's just drop this one. We can directly draw Okay, so these are terms up to x to the power of p, and it will continue up to infinity. So all these terms above p, we can write it in one term. So like t to the power of p plus 1. So the next higher order term. So this is some x bar. Okay, so this that term t to the power of p plus 1 is the p plus 1th derivative. We call it as at x bar. I'll just tell you what is that. So can be represented as error. So if you are only approximating it up to the x to the power of p, if you are doing only up to pth degree polynomial, then the terms that are left out here in general can be represented as plus 1th derivative evaluated at x is equal to p plus 1. And let me just, I think this is at x bar. So the whole thing is evaluated at x bar. I'm sorry, this also is x bar, including this one. So what is x bar? So if you are interested in the approximation, what happens over a small zone H? So if you call this as the size of the element over the element, what is the kind of error which you are committing? So that is x bar. So what is this x bar? X bar is neither x naught nor x naught plus h. So x bar is somewhere between x naught. So this is so this is what it is. So that means that we are approximating it with the pth degree polynomial. So any terms above this one which constitute the error, so are equivalent to the pf plus 1th derivative and x to the power of p plus 1, which is evaluated not x naught, but it can be anywhere between 0 to h, right? So it depends upon whether it comes here or comes here. So it depends upon where you are operating. Okay, so the error here, so that's what we are concerned here. So in the finite element approximations, obviously we are taking only finite number of terms. So that means that there are many higher order terms are left out, which will be accounted in this one. So what is the procedure of approximation? What is that which we want to achieve? So h, if it is the element size, so we want to make sure that as h reduces, as the element size reduces, we want error to become smaller and smaller. So this is our goal. As the number of elements increase, that is, as the size of the element decreases, so we expect that the error should reduce. So what is that? So let's just write down only the error. So error is p plus 1 derivative of phi. We are just only isolating this one, x to the power of p plus 1. So anywhere between to be more precise, I write it as x naught plus h. So this is what is the maximum then? Maximum error is when x, that's this h becomes, this x becomes h, and we write it as Okay. So in fact, you can write it as delta H here. Maybe to be more precise, if we want, we can continue like this one. You can continue to write delta XP here and delta XP here. And in which case it becomes the maximum value becomes H to the power P plus 1. So here this is evaluated at okay, so this is evaluated at x bar, so it's for P plus 1. And this value, so this evaluation of this derivative will take some finite value between x naught to x naught plus h. So the thing which depends upon h is only this one, h to the power of p plus 1. So this being constant, so over given a particular kind of function here, so this being constant, we say that the error depends upon h to the power of p plus 1, right? Error depends upon h to the power of p plus 1. So we say that it is the order of, so this is, that means that if h reduces, so the error reduces as h to the power of p plus 1. So we'll just discuss it just at this moment, just like that. And let us say that if this is in the function value phi x, but on the other hand, if you also take the derivatives here, if you are looking at the derivative of this one, so all these things will come out as, we can even write, so let us even, for simplicity, we can even write, for simplicity, we just write polynomial like this one. Okay, so if you take the derivative of this one, so what is the error in the first derivative? So you can say that this is a1 plus p to the power of x to the power of p minus 1, and the error here also will reduce by p plus 1 minus 1, right? So like this we can continue. So the rth derivative here, so if you are looking at the rth derivative of phi, so everything will come like this. P plus 1 minus r. Okay, so this is the error part. And continuing the same discussion, so error now in rth derivative is of the order of this one, h to the power of p plus 1 minus r. Okay, so the error is in rth derivative is p plus 1 minus r. So if rth derivative is occurring in your formulation, either in the weighted residual or in the variational formulation, so if that is occurring, so then you are committing an error of this order. So what is that which you want to achieve? So your finite element procedure should be such that what the error, so what should be, should decrease as h decreases. So what does that mean? That means that in this term, p plus 1, that means that p plus 1 minus r. So what should be this power? It should be at least a power of 1, right? If it's a power of 0, so what does that mean? So that means that it is constant. So error is constant with respect to h. So whereas at least it should be that this p plus 1 minus r should be equal to 1 or should be greater than 1. Okay. So that means that is okay. So this is p plus 1 minus r should be greater than 1, or what we can say that p should be greater than equal to r. So this is important. So whenever you make finite element approximation, you should make sure that your polynomial terms, which whatever you choose after should be p, and what should be p? P should be greater than r, greater than or equal to r. So for example, in your finite element approximations where you find this to be a linear first derivative, right, du by dx or d phi by dx, then the derivative is 1. So if r is 1, so the polynomial should be at least linear. The polynomial should be at least linear. And if it is more, what happens? If it is, this is minimum condition, right? So this is minimum condition. For example, if this is p plus 1 is, or if p plus, say it's 2, what does that mean? For example, if p plus 1 is equal to p plus 1 minus or whatever it is equal to 2, what does that mean? It means that, so h is, so the error is of the order of h square. So what does that mean? So that means that if h reduces to half, then error will reduce to 1/4. So it is half to the power of 2. So then error will become 1/4. So, or if h becomes 1/3, then error becomes 1/9. So this makes much more sense to use the higher order polynomial approximations. So if you use higher order polynomial approximations, then the error will reduce faster than the minimum most h to the power of h. So that is why, so we would like to use, so now in a particular element, you may require only a linear one, but then we would like to use a quadratic approximation because the errors will reduce faster. So say like it's h cube. Even if you take, say where you require a linear approximation, if you are using cubic, then error will be of the order of h cube, right? So what does that mean? If the element size reduces to half, then it's half to the power of 3, so 1/8. So the error will reduce by 1/8. So this is much faster. So that way it makes sense. That way it is useful to use higher order approximations. Okay, just to put it in a nutshell again, so we would like to have, now p should be just minimum is this one, minimum is p is equal to r. We would like to use polynomial more than r, at least one more than that, so that your error will reduce faster. Okay, so now let us look at how we develop higher order approximations for 1D and possibly for 2D. So let us do for 1D. So 1D, we are not really going into any particular application at this moment. So for two-term approximation, so this is of course for two-term approximation. So we have phi x as a plus bx, which is equivalently written as two nodes, 1, 2, right? So phi. So this we have seen. So this is equivalently put as shape functions, and the coefficients here are nothing but the nodal values. So here we know that either you can write it, or we can write n1 here. We know that it is x2 minus x divided by, call this as h. So x2 minus x1, or x minus x1. So this we have seen in one of the applications. So we can write this as x2 minus x divided by h. Okay, so this is for two-term approximation. So where the approximation here is linear. So if you go for, this is linear. If you go for quadratic approximation, so wherein this phi hat will have three terms, a plus bx plus cx squared. So which is obviously going to have three nodes, 1, 2, 3. So this is equivalently represented as n1, phi 1, n2, phi 2, and 3, phi 3. So this is for quadratic approximation, which you will have three nodes. So this can be extended for any number of, we can also do, this is for quadratic using three nodes. So we can also use for polynomial. So this can be generalized to pth degree polynomial. Generalized to pth degree polynomial. And if you want pth degree polynomial, so approximation by x will be, instead of a plus bx plus cy, so let's use a1, a2x up to a p plus 1 to the power of p. So pth degree, so instead of abc, I'm writing it as a1, a2, a3 up to p1. So this is equivalently, we'll put it as what? As n1 by 1 up to, so how many terms? So there are p plus 1 terms. So we have np plus 1 by p plus 1. So where n1, n2 up to np plus 1 are the shape functions, and where the coefficients are phi 1 to phi 1. So that means that we have 2, 3 up to p plus 1. We have p plus 1 terms, which will give you a pth degree polynomial, right? So this is how we have to convert this. And so we know that now here that this we'll assume a value of so this is phi 1, phi 2, phi 3 up to phi 4. So the procedure to convert these coefficients into these shape functions is just make them equal. So like these two, so phi is equal to phi 1 at x is equal to x1, right? So we can write this one as a1, or can I write it in terms of matrix? So we will write it in the form of matrix here, this P1 coefficients. So then we have phi 1. So if phi becomes phi 2 at x is equal to x2. So like this. So this is the first equation. This is the second equation. Right? So at the p plus 1, we have so the last equation is at the node p plus 1, we have, right? So we have like this, and so we can find out the coefficients here. So if you call this as some matrix C, right? So we can write the coefficients by taking this inversion. So this is the general procedure. This you can apply to any number of nodes. So what we are able to do here is that we are able to get the coefficients a1 to a p plus 1 in terms of phi 1, phi 2, phi plus 1. So what we can substitute here, so let's write this function phi x, this one here, as 1 x to the power of p right? So we are just trying to write this one. So these coefficients now can be written as C inverse okay. So what does this say? Now by multiplying this with this, and so we can write this one. So what will be the size of this one? So this is a one row consisting of p plus 1 components, and this is p plus 1 by p plus 1. So this is nothing but the functions so this is nothing but you formulate this coefficient matrix here, and then you take the inversion here and pre-multiply with this 1x, x to the power of p and so on. And then this is nothing but now here n1 by 1. So this n1 is a function of x. So you can see that this is how we can convert the original approximation here in terms of pth polynomial, which is made equal to in terms of the nodal values and nodal shape functions. And then these can be converted into this one systematically using a matrix of coefficients, where the C matrix is nothing but a matrix of p plus 1 by p plus 1 here. And so that you take the inverse and re-multiply with the polynomial terms. Okay. So this is how we can find out the shape functions. So there is also another way of finding out the shape functions. What is this shape function? So if you look at the definition of shape function, what is the shape function n1 here? The shape function n1 is a polynomial of degree p, and such that it has a value of 1 at node 1, and then it has a value of 0 at all other nodes. So we will just, for the moment, we'll break here and we'll continue and see how these shape functions can be directly written in terms of the polynomial of degree p. Okay, so we'll stop for here for this lecture.